Hi everyone, I am Ehsan Karim from University of British Columbia. The title of my research project is The Performance of Statistical Learning Approaches to Construct Inverse Probability Weights in Marginal Structural Cox Models, a simulation-based comparison. First, I will talk about some basic concepts. Then, I will explore the possibility to improve the marginal structural Cox model estimates. Finally, I will summarize the results. A variable is a confounder if it affects both treatment and outcome. When we have too many confounders, propensity score is a useful tool. To estimate propensity score, logistic regression models are popularly used. However, in the propensity score literature, it has been shown that the covariate balance sometimes improves if the propensity scores are estimated using the statistical learning approaches. Propensity score and inverse probability weights are functionally related. However, inverse probability weights can be generalized to incorporate time-dependent covariates. Sometimes such estimators are unstable. Therefore, various versions of weights are introduced to gain stability. As in the sample survey weights, these weights can be stabilized, normalized, and truncated based on specified percentiles. In longitudinal studies, sometimes confounders are also affected by the previous treatment. In epidemiology, they are commonly referred as time-dependent confounders. As the time-dependent confounder, L sub t is an intermediate variable as well as a confounder, adjusting or not adjusting for them both will produce biased estimates. In marginal structural model, the inverse probability weights are calculated first. Once such weights are computed, they are used to create the pseudo-population. This pseudo-population is free from time-dependent confounding, and simply adjusting for baseline confounders will produce causal estimate of the treatment effect. The weights are popularly estimated using logistic regression models. As these weight models are generalizations of propensity scores, many researchers hypothesize that the statistical learning methods may be useful in estimating the weights as well. Therefore, the objective of this study is to assess the performance of inverse probability weights estimated via different statistical learning approaches. As a secondary objective, we will also compare various versions of weights and corresponding truncations at various percentiles. To assess these, I simulated data using Young's algorithm to generate 1000 dataset suitable for fitting marginal structural Cox model. We calculate the mean squared error of the treatment effect estimate from the marginal structural Cox model for each version of the weights. Horizontal axis marks the weight truncation percentiles. Here we see that for the stabilized version of the weights, blue line representing the boosting method is performing better than the black line representing the logistic regression model. Exactly same statement is true when we compute the coverage probabilities. Let us move on to a real data analysis. The data is collected from the British Columbia Multiple Sclerosis Clinic. About 1700 patients were eligible and about half of them received treatment beta interferon. A few baseline confounders were present and relapse was considered as a time-dependent confounder. As the stabilized normalized weights performed well in the simulation, we only use these weights calculated from various statistical learning methods. Hazard ratios obtained from the marginal structural Cox model fit are similar for SVM and boosting approaches, but slightly lower than logistic regression. In summary, stabilized weights estimated from the boosting approach marginally outperformed the weights generated from the logistic regression. However, the computational burden associated with the boosting approach is much higher. The multiple sclerosis results from SVM and boosting are similar and consistent with the previously reported estimates. Here are some of the references. I want to acknowledge my supervisors and my collaborators from the BEAM study. I would also like to thank my funding agency, Multiple Sclerosis Society of Canada. Thank you for taking time to watch the brief description of my research.